Alright guys, so for today's tutoring session, I want y'all to have this in your notes. I'm going to go ahead and be recording this and posting it to YouTube, so if you want to follow along with these practice problems on your own time, you can. I'm going to run through 3 practice problems with you. For each of the practice problems, we are going to be looking at a mass spectrometry graph. So this picture here is a mass spectrometry graph. I'm going to write at the top, mass spec as an abbreviation. And for each of these graphs, we are going to be calculating 3 things. First thing we are going to be calculating is the relative abundance. So the relative abundance. Second thing is the percent abundance. And the third thing is the average atomic mass. So these are the 3 things we're going to be calculating for each graph. Before we get started, there are 2 parts of the graph that you need to understand. The bottom part down here, this is your mass. We can also call that as the weight in AMUs. And remember, AMU stands for atomic mass unit. These 2 numbers at the top represent the number of atoms of each mass. So here I have 79 atoms that weigh 24 AMUs. And here I have 10 atoms that weigh 25 AMUs. An important thing to remember is you will always need to calculate your total number of atoms. So always do that first. So when I look at my total atoms, I just add the numbers at the top of each bar. You have to add the numbers on the top because you want number of atoms. You don't want the mass. So this is 79 plus 10. So my total atoms is going to be equal to 89. So next I'm going to calculate the relative abundance for each isotope. I'm going to abbreviate this as RA. There is a formula that you are going to need to memorize for your relative abundance, and I'm going to write that at the bottom. So your relative abundance equals number of atoms divided by total number of atoms. When you calculate relative abundance, you are also going to have to calculate it for each of these masses. So this mass, my 24 AMU, this one needs a relative abundance. And this one down here that weighs 25 AMUs, it also needs a relative abundance. However many bars you have is however many times you have to do this formula. Because I have 2 different bars, I've got 2 different isotopes, I need to calculate the relative abundance for each isotope. So I'm going to plug my numbers into my formula. The top number is your number of atoms, and we already found the total number of atoms by adding the top numbers together to get 89. So this tells me that my relative abundance for the mass of 24 is equal to the 79 atoms divided by the total number of 89 atoms. So I am going to pull up a handy dandy calculator and divide 79 by 89. So plugging it into Google, because that's how things work nowadays, we get 0.8876, and I can round that up to 0.888. So this is my relative abundance for this first isotope. My second relative abundance, I'm going to do the exact same formula, but I'm going to be calculating it for my mass of 25. So my relative abundance of 25 is going to equal the 10 atoms that weigh 25 AMUs divided by my 89 total atoms. And remember, I got that by adding my 79 atoms and my 10 atoms together. So again, I'm going to plug this into Google because I love Google. Google is my friend. If you don't have a calculator, use Google on your test. That is going to give me 0.1123. I'm going to round that to 0.112. Put a box around this because this is my answer. So two relative abundances. This is 0.888. That's the relative abundance of my isotope that weighs 24 AMUs. The 0.112 is the relative abundance of my isotope that weighs 25 AMUs. I have two different bars for the two different isotopes, so I have two different answers. And if you want a quick double check on your work, the bar that is for the 24 mass isotope, this bar is higher. And if you notice, this number is bigger. Whichever bar has more atoms, that is going to be your bigger number. Whichever bar has less atoms, that is going to be your smaller number. So that is a real quick spot check on your work. All right, the next thing I'm going to calculate is the percent abundance. So I'm going to get a new sheet of paper. And to check these off, we just did relative abundance. This is the first formula on our list. Okay, I'm going to abbreviate percent abundance as percent A. This is so I don't have to write out the word the entire time. So whenever you're calculating percent abundance, you still have to calculate the percent abundance for each different isotope on this chart. So this line is going to need a percent A, and this line is also going to need a percent A. Since I have two different lines, I need two different answers. All right, so calculating percent abundance, you will need to memorize this formula. Percent abundance equals number of atoms divided by total number of atoms times 100. The one catch with this formula is I want you to do your division first. So I'm going to put that in parentheses. I need to divide first, and then I'm going to multiply. All right, so I'm going to calculate the percent abundance for my isotope that weighs 24 AMUs. So my percent A for 24 equals 79 atoms divided by the 89 total atoms. And as a reminder, I got this 89 by adding my 79 and my 10. That number goes in parentheses. and I'm going to multiply by 100. We already did this math, 79 divided by 89. If you look back at the previous practice problem, 79 divided by 89 is 0.888. If I multiply 0.888 by 100, I'm going to get 88.8%. And I need to do this one more time for my isotope that has a mass of 25 AMUs. So my percent A for 25 equals 10 atoms divided by 89 total atoms times 100. We already did this division when we calculated our relative abundance. I'm going to go back to that problem. We said that 10 divided by 89 was 0.112. And if I multiply that number by 100, I get 11.2%. So here's my two answers. My isotope that weighs 25 AMUs has an 11.2% abundance. And my isotope that weighs 24 AMUs has an 88.8% abundance. So we've calculated relative abundance, we've calculated percent abundance. Now we need to find the average atomic mass. I'm going to get one more piece of paper. All right, so average atomic mass has its own formula as well. And again, you will need to memorize this for the test. I won't be able to provide it to you. And I'm going to abbreviate average atomic mass as AAM. So your average atomic mass equals your mass times percent plus your mass times percent divided by 100. So this is a kind of complicated formula. What are we trying to calculate? Well, we're basically saying that we have a lot of atoms that weigh 24 AMUs. We have a few atoms that weigh 25 AMUs. These are all the same atom, but they have slightly different masses. They all have the same number of protons, but they have different numbers of neutrons that are giving them these different masses. We want to know if you take all of the atoms together and add up all their weights and divide it across all those atoms, what would be the average? So when you calculate average atomic mass, you are only going to get one answer. It's going to be the average mass for all of these 89 atoms. And it's going to be somewhere in between 24 and 25, but it won't be exactly in the middle. It's going to be tilted towards the mass that is more abundant. So our average atomic mass will be somewhere in between 24 and 25 AMUs. It'll be closer to 24 because we have more atoms that weigh 24 than 25. And we're going to use this formula to figure out exactly what it is. So I'm going to plug in my mass and my percent abundance that we calculated previously. So let me plug those in for you. Average atomic mass equals a mass of 24 AMUs times my percent abundance. If you remember, we just calculated percent abundance for this, and it was 88.8. If you need a reminder on how we did that, please rewind a little bit. Put this in parentheses. We are going to add that to our second mass, which is 25 AMUs, times the percent abundance, which was 11.2%. And we're going to divide that by 100. So now we need to simplify and solve. Okay, so again, pull out Google. We need to multiply 24 and 88.8. Times 88.8 gives us a huge number of 2,131.2. We are going to add that to 25 times 11.2. This number is a bit smaller. It's going to be 280. Remember, that's going to be divided by 100. I'm going to add these two together. So 280 plus 2,131.2 gives me 2,411.2, and I still have to divide that by 100. When I simplify, my average atomic mass for this element is 24.112. This is my final answer. So if I look on my chart, if we pretend this is 24, this is 25, and this is 24.5, halfway in between, my average atomic mass is right about here. This is 24.1. So if I added all these atoms together, the masses of all the atoms, and I divided by the number of atoms, I would get a number that's right about here, and that's my average atomic mass. This makes sense because most of my atoms weigh 24 AMUs, so my mass is going to be closer to 24. All right, last thing I want to do is identify this element. So I am going to pull up my periodic table. Get that open 1 second. So when you open your periodic table, move this up a little bit, you are going to see these squares. There's going to be a number at the top. There's going to be a letter, let's say it's X. There's going to be a word, and there's going to be another number at the bottom. And this is in every single square of the periodic table. It's going to have this format. This is your atomic number. It tells you how many protons are in the element. This is the element symbol. It's kind of a shorthand. The word at the bottom tells you the name of the element. And then that number at the very bottom, this is what's called the atomic mass. And whenever we're calculating average atomic mass, we are looking at these bottom numbers. We are trying to find the atomic mass that matches it most closely. So take a look at your periodic table. Try to find an atomic mass that is closest to this 24.112 that we calculated. And I'm going to look too because I have not worked this problem out ahead of time. I'm kind of curious. We are looking for 24.112. You may not find 24.112. I want you to find the thing that's closest. me 1 second to write down the answer. All right, guys. So the number we were looking for was 24.112. When you look at your periodic table, there's a few numbers that are close. But you should have found this element, magnesium. The number we were looking for was 24.112. It doesn't completely match the atomic mass for magnesium, but it's really, really close. The other elements around magnesium had masses that were 26.9 and 22.9. These are a bit further away from our 24.112. The closest match is going to be magnesium. So this element, the mass spec, based on our calculations, this has to be Mg. This is magnesium. And we have solved for our average atomic mass. All right, guys, I hope that broke it down for you a little bit more. I am going to wait till class to go over the next 2 practice problems because I wanted to show you this process in person. If you have any questions, please message me on Teams. I'd love to hear from you.